Okay, so welcome back to the classroom. Today we have a lot of little things to announce. 今天我们有很多杂事要跟大家报告。一样一样来。好，第一样，So the first thing is about the second midterm. The corrected exam sheet will be back to you on next Tuesday. So next Tuesday is the 9th of June. So in the lecture, I will give the exam sheets back, and you can check it out by yourself. And then in the recitation session, so it's in the same day, but from 5:30 in the room SC162. And the TAs will show you the reference answers. So please check the reference answers. Please compare it to your own answer first. And if you find the correction is not, is something wrong with the correction, or if you find the credit is not really fair, then you can just ask the TAs there in the recitation session. And I am quite sure most of the problems will be solved right on the spot, because the problems in the second midterm, they are more or less like standard questions or textbook questions, and there is actually, I feel a little sorry, actually there is not that much rooms for creativity. But then the result is that I'm sure the questions will be solved in the recitation with from discussion with the TA. And if you still have questions, then you can come to me on the 12th of June after the lecture. So this is how you do it with the second midterm. 我们下礼拜二会把期中考2的考卷发回去，在上课的时候发回去，所以请来领考卷。那下课之后，从下午5点半开始，会利用那个研习课的时间，然后在科3SC162，你就去那个房间，然后呢，3位助教都会在那边，那他会告诉你们我们改考卷的参考答案。对，那你先把你的答案跟参考答案对照一下。那如果你觉得你看完参考答案你还是觉得怪怪的，或是你觉得可能分数给的不太正确的话，那请你当场在那边跟助教讨论，然后呢更改你的分数，好，就当场，因为在当场3个助教都会在，然后他们3个人各自有分配的题目，所以请你找到负责改那一题的助教去把你的分数改好。好，那如果说你跟助教讨论之后，你还是觉得不太确定，还是想要再问清楚的话，那就是在6月12号星期五的下课时间12点吧，就是上完课之后下课的时候，你可以再来找我讨论。好，所以期中考2的题目，我是觉得有一点点抱歉啊，就是期中考2的题目我出的大部分都是那种很标准、有标准答案的题目，然后让大家发挥创意的空间比较小。对，那大家看考卷的时候可以注意一下，就是如果你写的答案非常的详尽，或是你还蛮有个人特色的，我有特别交代助教帮你多加分，所以你在看考卷的时候你可以注意一下。So the midterm 2, most of them are standard questions, but there are many students who just write a very serious essays with in the answers, and they have their own opinions, and they really did good researches and to give answers which has their own style, and I found it really good. So I just asked the TAs if they find excellent answers like that, and they give you extra bonus points on it. So when you get the exams, and you can check it out. Okay, so second midterm, and then then let's talk about the relaxing thing first. So on the 19th of June, I'm going to play a movie for you. So it's another movie because the last movie was very popular and students like it very much. So I decided to play another movie for you. And I think that's in the same TV series. It's also from the series of Ghost in the Shell, but that was played on televisions. So the character settings, the castings, and the story, the rhythms of the story, and the content of the story is a little bit different. But I like it really much. You can check yourself first before you watch the movie. That is called The Laughing Man， 就是攻壳机动队笑脸男事件。我看到有一些男生在偷笑，你们一定一直有在看，对不对？我觉得I find that TV series really really good, and I think it really fits your age because the main character, the mysterious laughing man is just like your age, and he showed a very to me when I'm at different ages and when I watch that story I have different thoughts. But in my age right now, when I'm looking at characters like the Laughing Man, I always think that, oh, I have to play this movie to my students and they have to watch it when they are young. So you can think about your positions in the society, and you can think about how do you apply your creativity, or how do you apply your power in a constructive way. So I think that is a very good movie. Just be the perfect ending of a long lecture. So let's play it on the 19th of June. And then we have to be a little bit hurry because I have to finish all the modern physics in 3 lectures. That is really difficult. Okay, let's do it this way. 所以我们6月19号我会再放另外一部电影，它也是攻壳机动队系列的。然后但是它很长 ，but the movie is very long. It's 2.5 hours. I'm still maybe I'll skip some of the introductory sessions and then let's just jump into the cases with the Laughing Man. So that could be our solution. 好，那个电影非常的长，就是2个半小时，但是我们上课只有2个小时。你们想要一边吃饭一边看电影吗？ Do you want to have lunch when you are watching the movies? So we can start from 10 and the movie ends on 12:30. Is it okay for you? Maybe if it's okay for you, please raise your hand. 是，就是那个电影很长。如果我们10点开始，然后会12点半结束，但是你可以带便当或是带早午餐来吃，这样你 OK 吗 ？OK 的人请举手。1、2、3、4、5、6。一直增值哎，等一下，1、2、3、4、5、6、7、8、9、10、11、12、13，好，14。然后就是两个小时要准时下课的人请举手，或者是12点之后没有事的请举手。哦。So what is the solution? What is the solution? Do you have lectures from 8 to 10? 你那时间没有人有课 What? Sorry. Then I have to choose. Then I would choose this one. I would choose this one. And but that would be a little bit pity because those students might miss the most important part. But it's okay. It's on internet, so you can check it out by yourself. 所以之后有事的同学，我会告诉你，就我当下我会告诉你那个影片的网址在哪里，你就可以自己把后面补完。好 ，OK， 所以这件事完成了，And final exam. final exam. So the final exam, I would like to do it in a form like a little research project itself. So we don't have any exams anymore, and I will give you articles. Those articles are some of them are the original paper written by scientists like Einstein or like Compton or like Anderson. I haven't introduced Anderson, but I will give you original papers like that, or some of the papers which are really modern, but the topics are very interesting. So please apply your knowledge in physics, which you learn in over the 1 year, and please write a review essay for the article. So now we don't have any bans anymore. Please just do it as the way you want, and you can discuss with each other, you can do collaborations, and you can be off topic or it can be over topic, and all of these are allowed and encouraged. No limitation, just do it in your way. But just one attention, one person, one report. So even if you do discussions and if you collaborate, but when you write the report, when you draw the schematic diagrams, and when you do the arrangement of the paper, doing the cover, things like that, and just one person, one report, because we give individual credits. 所以可以讨论，可以合作，可以离题，都可以。然后也可以进度超前，什么都可以，没有极限。但是唯一一条规定就是一个人交一份报告。那即使你是合作一起做的呢，还是请你写报告的时候自己写，因为我们最终期末的成绩还是一个人给的。然后我还是相信每个人都有自己独特的个性，所以请你展现你自己的独特的个性。And this is Chinese. I will upload these instructions on UE3 so you can just read it in Chinese. Okay, and we have 5 choices. Just pick one of the article. Pick your favorite one. So the first one is the discovery of positron, the positive electrons. And this is a very classic paper, but the way that he wrote the paper and the way that he designed his experiment is very simple, very clean and very elegant. So I'm sure you can just read it and you can understand it. So this is a very, very cute paper. I like it very much. It's written by Anderson. Yeah, he's a very, I think he's very famous in the particle physics field. And he, when he was detecting the radiations from the universe, the cosmic rays, and then in all of these pictures, and he discovered that one of the particle is spinning in a strange way. And he analyzed it, and finally he just claimed that this is a positive electron. So this is the beginning of antimatter. So this is a breakthrough in physics. And the second one is the discovery of Compton scattering. So this is another original paper written by Compton itself. So he is shooting light into atoms. And when he was detecting the reflected and deflected light, he just discovered that, this is so strange. Why the wavelength of the light changed? So this is a very important part, very important topic in wave-particle duality. So this is you can read his original writings, and you can understand how he designed the experiment and why he drew the conclusion that he can say light is quantized. So this is the second choice. And the third choice is the paper that I already mentioned. So this is for the students who are interested in biology. So our everyday life, who is interested in flowers and bees. So this is the electric potential on flower and how the bees react to it. So please read this paper. And this paper is published on Science. Science is the top of the top journal of all the researchers. But again, this is a very cute experiment designed in a very simple and clean way, but focused on a very important topic. So you can just read it and you can understand how he did it. This is an experimental paper. And the fourth one is the physics of structural colors. So this is why the butterfly wings shows such a metallic blue color. And here are many different kind of little animals, insects that got researched in this paper. So one of them is the butterfly, the other one is this is the interesting little bug, and they have a very metallic shell, and which shows different colors and rainbow colors. And they use the electronic microscope to analyze the structure of the feather and analyze the structure of the wings and analyze the structures of the shell. And they saw periodic microscopic structures on it, and then they just try to analyze how the light is diffracted or interfered by that microstructure. So this is a very, I'm sure it's going to be a very classical paper in the future. So you can read it you can read it now, but it's very long. It's 20 pages, so be careful. 就我还蛮确定这篇文章大概10几20年以后应该会变成经典，所以就是大家可以读一下这篇文章。它是用电子显微镜去分析蝴蝶、金龟子、孔雀，还有鸽子的羽毛啦、皮肤啦之类的微结构，然后它就是去解释说这些结构是怎么样造成了光的干涉跟绕射，然后呈现出这样子的颜色。但是这篇论文非常的长，20页，所以如果有心喜欢这个题目的同学，你要赶快开始动作。And finally, this is the hardest one. This is Schrödinger's virus. So Schrödinger just he just made a 我现在忘记反串文的英文怎么说。Schrödinger's cat. When Schrödinger was giving that story, that hypothesis, and actually he is doing it in a very ironic way. He doesn't mean that the Schrödinger's cat ever exists in nature. He is just trying to make a joke and try to show everyone how ridiculous the thought is. That is the Copenhagen interpretation, and Schrödinger doesn't like it. He would like to show everyone Copenhagen's interpretation is ridiculous, but somehow people take it so seriously. And they started to experiment and to show that maybe that is true. Maybe the Schrödinger's cat. So they start from Schrödinger's photons, Schrödinger's electrons, Schrödinger's atom, and now here's an experiment on Schrödinger's virus. So this is a paper he did. He did the experiment in a very difficult way, but he explained the theory in a very clean language. So I find it really good. So if you like hard topics and if you would like to understand what's really going on with Schrödinger's cat and Copenhagen's interpretation, and then you can pick this one. 所以对于那个薛定谔猫到底是怎么回事，然后还有哥本哈根诠释到底是怎么了，就是那个论战到底是发生什么事情，对这件事情有兴趣的同学，你可以读这篇论文。So we picked 5 papers, so you can pick one of them. 你可以选一个你喜欢的。And this is the contents of the review essay. So please just summarize what is the purpose of this research and what is the method applied in this research. What is the result? And then your own opinion. What are the good jobs in your opinion? What are the things that they do it in a very good way, you like it very much? And what are the things you find out, maybe this should be improved, I'm not very satisfied with it. So the good jobs and the bad jobs. And finally, if you take this research over, and what would you like to do? So if you continue with the work, if you start to do the work by yourself, and then what are the things you would like to do? 这边，然后这比较重要，我用中文讲一次。所以你的评论，请大家撰写那个学术论文的评论。然后评论的内容呢，第一个1到3是内容的摘要。首先是这个实验的目的，再来是方法，最后是实验的结果。讲重点就好，不要写得落落长，然后也不要 copy and paste。 那个是会很明显的，就是请你讲重点、目的、方法、结果。然后呢，再来就是你个人的意见哦，4、5、6应该要占最多的篇幅就是第4是你认为这个实验做得很棒的地方，就是我们觉得哇太赞了，怎么这么聪明啊？哇太赞了，怎么这么仔细啊之类的，你可以写出你认为他做得好的地方。然后再来是你认为觉得不太对劲，或者是不错啦，但是可以再改善的地方，然后你可以把它点出来。最后呢，就是如果你接手他的研究，就如果这一包就交给你，你要继续往下发展的话，你想要往哪个方向发展？为什么？你要怎么做？所以第6个部分，你就是可以完全就依你的喜好，然后就依你的喜好来写。And then here are how we give the credit. So we will be giving levels A, B, C, D, and then we convert it into the 100% credits. So if you're here, we just set this is the basic structure of your report, and if it's incomplete, which means here are the 6 assignments, and if some of them are missing, and then you get 60. You get a D. If it's complete, you have a C. And if it's complete and thorough, which means that you do it in a very, very careful way, and you're very mindful with all the details. If it's complete and thorough, you get 80. If it's complete, thorough, and with your own opinions, then you can have an A, which is 90 credits. And depends on situation, depends on different kind of situations, and then sometimes we give a plus. So this is how we give the credits. And you can write it in Chinese, you can write it in English, both of them are okay. If you write it in English, which is very challenging, but you can get an upgrade of your credits. And you can do it in handwritten, or you can do it in electronic formats. I strongly encourage you to do it in electronic formats, because you can keep it, and then if you have, I'm sure you will have some occasions that you will need it later. And 6 pages of A4, 6 pages, so one, maybe I should show it, otherwise you ask me over and over again. 我示范一下，不然就一不会。This is 1 page, and this is double paged, so this is 2 pages. 就是这样子是1页，这样子前后正反是2页。好，总共不要超过6页 A4， and the font. The size of the font, the size of the size of the schematic diagrams, and you can just do it in just as you wish. So we don't have any limits on it. 字形大小啦，然后什么图的大小等等，我就没有规定，你就是你就自己排版，你觉得看起来舒服就好。你要用32号字体，我也没有意见。好 ，and okay, so this is in Chinese. And okay, so this is the final exam, and the deadline is. Oh, sorry, I have to change. This is 20. This is not right. Sorry, this is not right. 23rd. The due is 23rd. 23rd. I forgot to change it. That is the due last year. So the deadline is June 23rd. June 23rd. June 23rd. So 2 weeks later. No. Yeah, 2 weeks later. 2 weeks later. 23rd. And we will be here in the classroom, and then you just give the report back. Okay, so this is a deadline. Just mark yourself. So I have to change it. are here. Let's switch it to English interface. So this is our new E3, and just go to content. Here's a folder called final exam. Just get into it, and this is the instruction. Here are the 5 papers. So you can just pick one of them, download it, and start read it and start write the report. 好，正在直播中。And finally, here is a little chances for bonus. We just did a bonus experiment for the monopole motor, the electric motor, and most of the students just done a really good job. So if you already did the experiment yourself, I'm sure you already write the theories of it. So most of the students do it in a really good way. You already have the theory of it, and you did it by yourself, so you know the method, and you get the results like your pictures and your videos. And if you have extra time, and if you want to, if you need to, you can write a report for it. So this is for bonus. This is not compulsory. But if you want to do it, you can do it. Then if you write a report, you can give it to me. I will correct it, and I will give you a recommendation later for you as a cover for your report. 那个，你如果之前有做那个电动马达的实验的话，那如果你有空，如果你有需要，你想要，那我也非常欢迎你把这个小实验的报告、研究报告，你把它写完，你把它写完成。那也是一样，在6月23号以前，就是你跟着 final exam 一起交回来。那我会改你的报告，然后呢，最后我会附一张推荐信在你的封面上面，我会在上面写明说你上课的特质啊，还有你做实验的时候展现出来的技能啊，还有你的这篇报告哪里写得好，就是这是一个推荐函。那我相信接下来有一些同学可能想要当交换学生，可能想要申请奖学金，可能要申请企业实习等等，那这个东西对你是会有帮助的。所以如果你有这个需要，那你可以把这篇 report 你可以把它完成拿来给我，然后我会给你一个推荐函。好 ，so this is the bonus, and of course you get the bonus credits for your final rankings. 那当然也会帮你再加分，加分会再加码。那就看你报告写的怎么样，就看你加几分。好，所以这部分是你就是加分题，好，也不是强迫一定要做的。Okay, so I'm sure the students maybe in the following years you would like to apply for exchange students. You would like to apply for a scholarship, and you might be applying internship in industry. And if you have a recommendation later, and if you have a complete work like this, a demonstration like this, then that would be very good advantages for you. So if you want to do it and you can do it, I will give you a recommendation later with your report. 好。讲完了。喘一下。再来。好。稍微等我一下啊，我转换一下心情。Last time we introduced diffraction for structure analysis. And we introduced the famous experiment how we use X-ray diffraction to analyze the structure of a DNA, right? So this is diffraction, and now we are going on with the double slit experiment. The double slit experiment is kind of a milestone in modern physics. So let's just watch a video on a realistic double slit experiment. 我们来看一个很有
谢谢小金管给我满满的胶原蛋白，红毯持妆一整天，一起体验小金管吧。
我们来看很有现实感的双颊峰实验。
What is light?
What is light? What is light? That's a good question. What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are. It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The color. It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right?
Yeah.
It would be.
这个中文翻译 aura 就是气，就是你看一个人那个气质、那个感觉、那个 feel， 那在英文里面有 aura。
The difference, you see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes, smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
You can take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom? Well, the obvious thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box. Two bright bands.
Two little lines. Yeah, I think it'll be one line for the two.
I'd be expecting the whole box lit up.
That'll probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No,
I see dots.
How many?
it's one circle.
Oh, there's one in the middle strongest, two either side.
And the two on the outside are multicolored, and the one in the middle is just white.
Kind of a rainbow.
The rainbow of color as well.
Quite a few colours, but lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that
On
way.
either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits. That's incredible.
Well, all we're doing is we're putting a light through two very narrow slits side by side. So how does this make any sense?
The
there's some kind of principle involved that the average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light cancelling itself out.
This is basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Exactly the same.
They go and overlap. As this ripple overlaps with those ripples, down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, then a dark spot, then a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. So you saw the ones to the right were slightly colored.
Yeah,
that's because the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences, different wavelengths.
Exactly.
That's amazing.
So the difference between
So that red bit over there, the green part, is just, I'm seeing
It's
that,
a
it's just different
different
wavelength. And that's how we bring in all these beautiful colours all around us.
Exactly.
That's amazing. I'm amazed. Oh, good on you, thanks, man.
Hey, thank you.
I have been enlightened.
So this is a very nice YouTube channel, you can watch it. 这个我还蛮喜欢自己这个 YouTube channel 的，可是这位 YouTuber 他会做很多非常有趣的实验，有些蛮难的哦，对，然后你可以去看。I love this YouTuber very much because he get into the labs and do interviews with great scientists, and he did experiment by himself, and it's not a boring experiment like in the lab in the universities. It's not a boring one. It's a very interesting one. So I really recommend you to subscribe to it and watch his video. Okay, so you can see the analogy between light and the ripples on the water. And here we have to do a little bit of mathematics. So here you can see that was his demonstration with the ripples on the water, and this is the sources of the wave. And here we just define the top of our wave, the maximum of our amplitude is the wavefront. And if you draw the wavefront, and then if you do additions and subtractions, and then you can see that we have fringes. And here we have to do the analysis with the position of the fringes, and this is how we do it. First of all, we define the distance delta. So why we define it this way? Because we would like to, first of all, we fix ourselves in a position. You can imagine here, this is the position where we put the detector for the photons, and we just try to detect the intensity of the light. And this is the center of the 2 slits, and this is the line which is normal to the plate for the slits. And we are standing here and we are measuring the intensity of the light from the double slit. And this is the angle. So you just draw a line here. This is the connection between the center of the slit and yourself. And then here, this is the angle between between these two lines. And here we can study the geometry a little bit just by principles of trigonometrics. Then you just know that this angle is just exactly the same as this one. Okay. And if you compare the distance traveled by the light number 1 and light number 2, the distance from here to here, this is the distance of the distance traveled by light number 1, and from here to here, this is the distance traveled by light number 2. And here is the delta, is just a difference between the two distances. So this is the optical path difference. Optical path, and this is the optical path difference. And we already know the distance between the slits, which is d. Then the optical path difference is d sine theta. I think everything about diffraction and interference is the question about optical path difference. So the key point is how do you analyze your geometry, and how can you find the optical difference of your rays? So that is the essential point of diffraction and interference. 那我觉得任何跟那个绕射跟干涉有关的问题，它的关键点都是在于说你能不能够把 optical path difference 找出来。对，所以你要先分析一下你的整体设置的结构，然后你要找出来说你的 optical path difference 在哪里。你只要能够把你的 optical path 辨认出来，就会很简单了。对，那就是我们基本上做光学实验的时候，关键点都在这里。And we focus on the position where we get the largest intensity of light. This is the bright fringes, 就是亮纹的地方。Fringe 就是边缘或是一条线这样一条线，那个你可以叫它 fringe. And this is the position of the bright fringes. And for a constructive superposition of light, the optical path difference should be an integer multiplied by the wavelength of the light. 就是你如果想要得到一个建设性的干涉，就是两个光的波叠加在一起，你的 amplitude 要变大的话，而且是最大化的话，你的 optical path difference 就要等于整数倍的波长。So this is the logic, and this is how you set the condition of constructive interferences. And m is an integer. It can be 0 and plus or minus 1 and 2 and go on and go on and go on. So you have many conditions. And all of them satisfy the requirement. And practically, usually we measure the distance here, the y, and we measure the length L here, and we convert it to the theta. And depending on if you are very close to your slits or if you're very far away of your slits, and then you apply different kind of approximation. So that is another matter. 在实物上，我们会再细分成两种典型。第一种典型是你的萤幕跟double slit的距离很近的时候，那个时候球面波就是球面波，你就是要认认真真的把它当球面波。那如果说你的 L 很大，就是你的萤幕跟双颊缝间距离非常远的话，那你就可以用小角度近似去处理它。所以主要是这样的差别。So I just explained that. The near field and far field diffraction. The near field is the cases when your screen is very close to your double slit, and you can't ignore the fact that your source is a spherical wave. That is a near field diffraction. But if L is very large and when the screen is very far away from your double slit, and approximately you can treat your wave as a plane wave anyway, and then you can use the little angle approximation for all the angles. So that is the far field diffraction, the Fraunhofer diffraction. So, but that is the next step. Complicated next step. That leads to Fourier optics or Fraunhofer optics. 这个就在我刚刚讲的那两个就会分裂成光学的两大分支，一个是傅里叶光学，就近场光学，还有另外一个是法赫特光学，就是远场光学。他们你就觉得分裂这样，精神分裂，就是一堆人之间就很近，一堆人之间就很远，然后中间就是很难处理，不好处理。好，我现在有点赶了，不能讲太多废话。Okay, and double slit interference. Okay, so we just get into the cases with the bright fringes, and for the dark fringes, for the places where the interference is destructive, 就是上去的波跟下来的波两个会消掉的那个 case. The condition is like this. So if your optical path difference is just equal, here is a wavelength. But here's the multiplication, and here we have the 1/2. So this is the half integer of multiplied by a wavelength. 就是半整数，就是 therefore. So if it's a half integer multiplied with a wavelength, then if it just matches your optical wavelength, and on that position, then you will have a dark fringe. So the light just disappeared. And you can understand why, because a wavelength is a up and down. And if two waves are shifted, and if the phase shift is 180 degrees, this is a phase shift of 180 degrees, and you have a disruptive interference. 那你可以想象那个半整数的意思就是波的一半。如果两束光，你这里有两束。然后它们之间的光程差刚好是半个波长的话，相位两个之间相位差就是1/2个波长嘛，180度。那么这个就是它们彼此之间叠在一起之后，你的光就消失了，破坏性的干涉。好 ，so this is how you analyze it, and this is how the position of the fringes is related to the distance between the slits. And here are some applications, useful applications, beautiful applications. So if you see the bubbles, the soap bubbles, and actually soap bubble is a very important topic in surface science. There is a lot of people doing researches on soap bubbles about surface science, because soap is kind of a thin layer of fat on the top and a thin layer of fat on the bottom, and then we have water in the middle. And in that kind of configurations, then we have air, fat, water, fat, and air. So here are 5 layers of thin film, 5 layers of media stacked together. So we have many the light. When the light is going through such a thin film, and then they have very complicated transmission, reflection, refraction, interference. We don't have diffraction here. Yeah, we don't have diffraction here. We have interference here, and the interference here is determined by the thickness of your film, and therefore we have different colors. So you can see that here is oil on the water. So if your oil have different thickness, and then you have different colors. And here's a very nice demonstration. So this is a circular rack, and we have soap films on it. 这个是肥皂膜，就是你用一个圈圈去浸那个肥皂水，然后就这样放着。And then if you look at the colors through the film, and then you can see that from the top to the bottom, and the colors are changing. They are changing in a sort of regular way. So we have dark, very dark, purple, blue, green, yellow, orange, sort of red, a little bit of red, and then magenta, 就是洋红色、桃红色。And then we'll get back to the blue and cyan and green and yellow. You can see the periodicity of the light, isn't it? and you can see that here the colors are fading. So this is a very vivid color, and here the colors are kind of, they get softened and they get mixed together. And this is because of the thickness of the film. So here we have thin film, and here the films are thicker. And if the thickness of the film is more or less the same as the wavelength of the light, and then you can see a very clear color from the interference. And if you have thick films, then you can think about it. If this is the thickness of the film, and this is the wavelength of visible light, and then you have many different kind of combinations for the constructive and destructive interferences in it. There are so many possibilities. So if you just add all of those possibilities up, you have many colors. So all the colors are mixed. So that is a qualitative explanation to it. 所以我这边很快的定性解释一下为什么事情会这样。你可以想象哦，就是如果一个肥皂泡掉在半空中，然后呢，慢慢的上面的肥皂泡会很薄，但是垂在下面的肥皂泡会变厚，因为重力嘛。那假设说你的肥皂泡的厚度，就肥皂泡是一层油脂、一层水，然后一层油脂夹在中间，它是一个3层结构，甚至多层结构都有可能。那如果说你的厚度跟可见光的波长差不多的时候，可见光的波长大概就是几百 nanometer， 在400到700之间。假设说你的厚度就是在400、700那边的时候，那么你的干涉条件就是非常清楚的，对吧？就是符合你的干涉或者是干涉条件的，可能就只有那么1组、2组光程差会符合你的条件。那这时候你的颜色呢就会非常的清楚，就是那个颜色非常的鲜艳。可是当你的薄膜厚度变厚的时候，你可以想象一下，如果这是薄膜的厚度，那如果这是光的波长，你要把那个光这样塞进去，然后你要去想出各种光程差的排列组合，你是不是会找到很多组符合你的期望的条件？很多组符合你的期望条件，就表示有很多种波长都符合你的期望。这么多波长全部加在一起，你的颜色就越来越混，越来越混，就越来越接近白色。所以这个是定性的说法。这个想法在工厂里面非常的好用 ，because this kind of qualitative thought is very useful when you are working in industry. Because if you are working with silicon wafers, if you're working with silicon wafers, and if your fab is creating a lot of silicon wafers, and this is a stacking of so many different thin layers, and then you can see that kind of interference too. And then you can just, if you're very experienced, and then you can just tell someone, and I think the thickness is maybe for a film like this one, I would say the thickness is about one micrometer, and this is a few hundred nanometers. I can just directly say the thickness, the ranges of the thickness, just by seeing the colors. See if it's very bright and very saturated, or the colors is softened and the fadings, and then you can just tell the operators, and you can just tell your colleagues by the colors. And you don't need to send it to a lab and wait for 3 weeks for the result. You don't need to. You can just look at the colors, and then you can say about it. And if you have a lot of wafers, and some of them are very colorful, and some of them doesn't have any color, and then you have a very clear idea about your machine is not working well. Because when it's producing a lot of wafers with different kind of thickness, and of course there are big problems, isn't it? So this kind of synthesis in physics will help you a lot when you are working in industry and when you're working in fabrications. 这个像这样子的感觉，这种 sense， 你在工厂里面说超好用的，因为你只要一看你的细晶圆的颜色，你马上就可以说，我觉得它的厚度应该是700 nanometer 之类的。你看一下颜色，你就说，这个厚度不行，太厚，我觉得应该 差不多几 micron 了，等等等等，你看颜色你就知道了。然后呢，你可以马上做一些快速的决定，尤其是你在工厂里面的时候，你那个silicone wafer是用喷的，是用喷出来的。你如果觉得有什么事情不对劲，你要马上下决定，没有时间等待你说把一片 silicone wafer 送去电子显微镜等3个礼拜，然后告诉你说这厚度是多少，没有时间。对，但是如果说你对这种颜色啊、干涉光啊，然后你很有概念的话，你就可以你可以在很短时间之内，你可以下很正确的判断，然后你就会变成一个很重要的人物。好，silicone wafer 是这样。And if you are working with anything about cells, for example, this is if you are working with cameras, you have to work a lot on 2 layers of glasses, and something is in between. So if you are working in camera industry, in liquid crystal industry, or if you are working, especially in biomedical industries, because you have to create a lot of samples with glasses and with your samples sandwiched in your glasses. And you can just look at the pattern of your fringes, and you can just look at the colors of your fringes, and you can tell if my sample, the thickness of my sample is right or not. So if the thickness is very evenly distributed, then you don't see that much color. And if you have things like that, then you can almost say that, okay, so here this is very thin, and somehow it gets thicker outside, and something is wrong with my production of my samples. So this is a very, very important technique too. 然后这个是，如果你的工作，尤其是在那个生物医学相关的，这个技能是必备的，因为你可能会一口气要做很多个玻璃饰片，然后那个玻璃饰片都是2片玻璃，然后中间夹着某某东西。对，大家都是水溶液啦，水溶剂型的东西。那如果是液晶萤幕的话，中间就是加液晶；如果是 Google Glass， 中间是加液晶；如果是手机镜头大力光，然后或者如果是什么数位相机的话，那么它的成分就会比较复杂，它就会有很多 coating。就比方说我要polarized coating， 然后或者是防撞 coating、防刮 coating 等等等等，都会有很多薄膜。那只要有薄膜的地方就会有薄膜干涉。那你可以看那个干涉条纹去判断说我的薄膜有没有，我的厚度是不是一致。假设说它的厚度不一致，有的地方很薄，有的地方很厚，你就会看到一圈一圈的这种条纹。那假设说它的厚度是非常均匀的话，你就不会看到。所以你可以从这些颜色的分布呢，很快就可以判断说这个东西到底 OK 还是不 OK。OK， and here is some remark for you. And honestly, I find the optics inside a little bit complicated, so it might take some time for you to understand what's going on. So here we have to talk about the changes of phases of light reflected by surfaces. So here is the cases that if we have 2 medias, N1 and N2. N1 and N2 are the refractive index. So if N1 is smaller than N2, so the light ray it goes through N1 and wants to go into N2, but on the surfaces the light gets reflected anyway. And in these cases, the light will have a 180-degree phase shift. 就是你如果 N2 比 N1 大，你可以想象这是一个对光来讲，这是一个要产生共振的话 ，N2 比较沉重。比较不容易产生共振 ，N1 比较轻盈，它比较容易产生共振。You can think about it with the resonance of wave. So, a large N2 means that N2 is heavier, is very sticky for the light, so it's very hard for the light to. What's going on? It's very hard for the 那好，回复正常了。It's very hard for the light to initiate the resonance in N2, and it's easier for the light to initiate the resonance in N1. And in that kind of cases, the light will have a 180-degree phase shift. And here's the analogy to the vibrating strings. So we can think about the vibrating strings, and the vibrating strings with a fixed end on a rigid support. They will have exactly the same behavior. And the light as a wave, they will show exactly the same behavior. So here's a comparison for you. And on the other hand, if the light is going from a heavy media into a light media, but on the surfaces it gets reflected, some part of the light is getting reflected anyway. But in that kind of cases, light is easier. For light, it's like I'm free and it's getting into a media which is very easy for me to vibrate. And then this is the cases like a string wave go to a free support, and this is loosened so it can move up and down. So we can see the comparison here. And in this kind of cases, the light just simply get reflected and there is no phase shift on it. So here are the differences with the light traveling in media and if you have an interface. The problem is from the interface, and the problem is from the differences between the refractive indexes. 好，这边的重点就是呢，你的光如果说它穿过两种介质，然后两种介质的折射率不一样的时候，你就要注意哦，就是我是从折射率小的进去大的，还是从大的进去小的？如果你是从小的进去大的，那你的光在被反射的时候就会有180度的它就会相位会反过来这样，所以差180度。这个是最重要的重点，这件事情是关键。如果你记得这件事情的话，你就会知道虹膜干涉是怎么产生的。And this is how you set the condition for a thin film interference. So it gets more complicated, isn't it? 所以你看到这个图就哇，怎么这么复杂？是的，它就是这么复杂，有点麻烦。So we just look at here are 4 passages of light. And the passage number 1, this is a light going in, get reflected at the first surface. And this is the case when we have 180 degrees of phase shift. Okay. And then if the light goes into, this is the transmitted light, it goes through your thin film, but on the second surface it gets reflected again. And this is from a heavy media into a soft media. So here we don't have any phase change, and here it just gets transmitted. So the light number 2, and there is no phase change at all because of the passage. Okay, and here is the line number 3, and here is the line number 4. And if you are detecting the interference at the back of your sample, then you have to analyze 3 and 4. But now let's focus on line number 1 and 2. And here is the approximation. We just take that the thickness of the film is very, very thin. So the optical path difference is approximately equal to 2 times of the thickness. This is in and out. And of course, if you really care, and then you can add a angle like cosine theta to it if you want to. So you can derive it by yourself. Now 大家要注意，这里的推导里面有一个简化。就是呢，我们就想象你的 T 非常非常的薄，那我们在算那个 optical path difference 的时候，我们就直接把它当2倍的厚度就处理掉了。但如果是有一些同学很细心的，或者是你的状况其实是处理这种光是这样进来的，就是斜向这样射进去的，那你就要考虑一下，就是你还是会有一个角度 然后你就是要把那个长度apical path difference 这样进去。对，那你要花一点时间去分析你的 geometry， 你要把实际上的 apical path 你要把它好好的把它算出来，这样会变成 arc。你知道横的长度吗？这样会变成 arc 什么 arc cosine， 这样会变成反 cosine。好 ，anyway，but then the principal will set the condition. So here we have light number 1, which has a 180 degree of phase change, and here we have light number 2, and the optical path difference is 2 times of thickness. So if the 2t somehow just matches the 180 degrees of phase change, then they will have a constructive interference in the reflections. Okay. Therefore, here are 2 sources for the optical path difference. One of them is the phase change due to the interfaces of media. The other one is the real optical path difference. 所以在薄膜干涉里面，我们现在那个光程差有2个来源哦，一个就是光实际上走过去的距离，这个是没有疑问的。但是你还要再考虑一件事情，就是你的光在穿越2种不同介质的时候，它会有相位差。好，所以这个相位差你要把它考虑到 optical path difference 里面。And here is how we set the conditions for the reflections. This is in the textbook, so if you get the principles, then you can derive it by yourself. So I don't go through it anymore. 这个你可以看那个，因为你现在已经知道关键点了嘛。那接下来我相信你可以自己推导，课本上面也有，所以呢你可以去看。好，那这边我就不再特别多说了。And here is a very famous. This is the Michel Levy birefringence colors. 这个是在光学上面或显微术上面非常经典的一种手法。So this is a very classy technique in microscopy. So you can see that you have it shows different colors. Of course, there are constructive interference, destructive interference. So some of the light is intensified, and some of the light is weakened. And all of these mixtures of the light creates different colors. And the thickness in nanometers, so 0, this is almost nothing. And from 400 maybe here, and to 700 is somewhere here. This is the band of the visible light. Okay, so here. And if it's like 1000 nanometers, so this is 1 micron. So this is the thickness of most of the biological films. So most of the biological films are here. And if you go into nanotechnology, then you will see the colors like this very much. 好，那这就是你在你的薄膜如果是不同的厚度的时候，你就会看到不一样颜色的 view， 就会有不一样的感觉。可以先跟大家说一下，如果你平常工作的范围是那种生物组织、皮肤之类的，你会看到的颜色范围大概在这里。那种粉粉的感觉。那如果你工作的范围是纳米元件的话，然后一个很薄很薄的薄膜的话，你就会很常被这种颜色闪到，就是这种，这里大概是 nanotechnology 的范围。好。And then you can see here are the scales of the thin film, and then you can compare it to the colors. So you know that, wow, actually our soap film can be from a few nanometers to a few micrometers. So, wow, they have a very, very wide order of magnitude. So this is a very good example. And here's Newton's ring. So this is a model for the Newton's ring. And just as I said, if you have sort of bumps on your thin film， 就是你的薄膜上面如果有比方说一个凸起来一块，对，那个叫 bump， 那种凸起来一块，那你在显微镜底下，或者是你这样眼睛看，就会看到牛顿环。And the Newton ring is just the thin film interference that we just introduced, but because of the bump, here are so many different thicknesses. So here are different conditions which result in a series of dark and bright fringes, but generally they are circular. So if you have a circular Newton's ring, then you know that your bump is a dot. And if it's a line, if it's a irregular shaped, and the rings will be irregular too. 通常在应用上面啦，我们会看牛顿环的形状。那你的牛顿环如果是一个这么完美的圆形的话，我们就可以确定你的脏东西裂拍米亚应该是一个点，就是一颗灰尘之类的。但是如果你的牛顿环是那种歪个几撮，然后歪七扭八，然后左右还有的粗有的细那种，那就表示你的排米亚应该就是很乱。对，这是我们大致上判断的原则。And if the fringes are wide, which means that the variation in thickness is not very serious. But if your fringes are very thin and very clear, and then which means that the variation in thickness is very sharp. 就假设说你的牛顿环只有一点点，然后条纹之间的距离也是蛮远的，我们就觉得没关系，要放它过，我们觉得只有一点点而已，不要理它。但如果是像这么清楚的牛顿环，超清楚的这种，那你应该就是入城了，应该是蛮严重的。对，那这个就是大家就不能接受。好，那这也是基本的判断原则，可以给大家参考。Okay, so this is about optics. 让我休息一下。And today we'll have a special event. If you remember, in the first midterm, we have a problem that we said that if we have a wire which carries current, and what is the distribution of electric potential and electric field from the wire, isn't it? And then we just draw the conclusion that it doesn't have any electric field, and I just set up a little analysis for you and show that the distribution of the voltages and its boundary problem. The shape of the distribution depends on your boundary condition. And here is our student Roger. He just found a paper who analyzed the electric field from a wire, and they have different opinions, and they find some other physics in it which gives the electric field from a current carrying wire. So he is going to give a little report on it. So that's just so Roger, this is your turn. How?
我要用麦克风哦。
要啊，
好。
不然你一定少加。
Okay, today I'm going to talk about the electric field outside the stationary resistant wire, which carrying a constant current. 会坐着吗？
可以啊。
好，谢谢。So, the myth that there's no electric field outside the wires come from 3 reasons. And the first reason is the stationary resistant wire carrying a constant current is essentially neutral in its interior and along its surface. And this is the major myth, major reason that it leads to no electric field outside the wire. And the second reason is that they think that magnetism is a relativistic effect, but this is something that including the relativities, but my knowledge is too little to understand this, so I'm not going to talk about this. And the third reason is that some famous physicists like Maxwell, they condemn that Weber's electrodynamic experiment have totally invalidated. And this guy Weber's, he just wrote a paper that the paper told the wire has a first order force and a second order force, but he did not do the experiment. He just came out the idea. So Maxwell told that there's no experiment support Weber's theory, but and he also told that the experiment shows that no electric field outside the wire. But here's the experiment bring out by Jimmy Manco, and he just do the experiment and shows that Weber's theory is correct. Okay, here's the geometry of the problem, and this is a 3D. Here's a 3D picture. So it's respective to R and Z, and the theta. The theta is here's the curve. So the theta is here, theta, and it's just the theta is the okay, this one here, and the theta is here. Okay, and
maybe you can explain what is this and what is this?
Oh, this one is.
And the theta is between what and what?
Okay, so everyone understand it. So, and the Z, here's a Q. This is the test charge outside the wire, and the test charge is the distance between the test charge and the middle of the wire is Z, and the R is the distance from the Z-axis and the Q, and the length of the wire is L. So here is L over 2, and this is minus L over 2, and the potential on the minus L over 2 is low L, and the right side is low R. Oh, and the radius of this wire is A. Okay. So consider a loop like this one, and the electric field is follow the geometry like this one. So this is the electric field, but if I bend this loop into a curve like this one, and the electric field will follow its geometry, but the battery isn't changing. So there must be something changed along this wire that creates the electric field. And the only thing that's changed is the distribution of the charge, the surface charge along this wire. So the battery did not generate the electric field directly. It just, the role of the battery is maintain a distribution of the surface charge, and the surface charge will generate the the electric field.
Do you mean the distribution of charges is not regular? Some of the places we have a lot of charges, and in some of the places we have a little bit.
And here.
它的意思就是你在那个电线上面的电荷分布不会是均匀的。如果你的电线是有弯弯曲曲的时候，就有的地方你的电荷密度会变很厚，有的地方你的电荷密度会变得很稀薄。好 ，OK。
And here's the conclusion of another paper, but I cannot find this paper because it's the paper of 1968, and I can't find it. If someone can find it, please tell me. So the potential and the surface charge distribution is the linear function of z, and z is the distance between the test charge. And here's this one is the density of the charge, the surface charge. Okay. Oh, and this is low A. Low A and low B is the constant. So because we got the surface charge density, so we can integrate the charge and we can get the potential. And here's the potential. And we differentiate the potential, we can get the electric field. And the electric field multiplied by Q, the test charge Q, we get the force. So here's the conclusion. Okay. So this is the circumstance of the long straight wire, but here's the bent wire. And the bent wire, the force generates to the Q. It will be the centripetal force. So because he also calculates the Hall effect, but because the Hall effect is too small, so we can ignore the Hall effect. And here's the force. And because here's the Vd is the drifting the velocity, and we can change it into I, so we can get this force. Okay, and this is Jeff Fimenko's experiment. He just the L over A is 40 over 3, and the low A is the low left is minus low R. So it means that the middle point, the potential of the middle point is 0. So you can see that electric field is like this one, and the potential is this. Okay, and
the electric field, is that showing the strength, or what about the direction of the electric field?
Direction is like here or here, but
is the direction along the line? Is the direction along the line?
Yeah, along the line. And I forgot to talk about this. So if you put R, the potential of the right side and the potential of the left side are the same, and the I is 0. So what do you get? You get a charge wire, but with no current inside. And if you put the number in it, and you can calculate it, and you will get the same answer we got from the Gauss law. Okay, and here's the conclusion. Okay.
I think this is the most important part of your review. So can you introduce it?
Oh, okay. So the textbook tells us that the electric field was generated by the potential, and the potential was given by the battery. But actually, the electric field outside the wire and inside the wire is given by the surface charge. And the role of battery is maintain the distribution of the free charge along the surface of the wire. And electric field outside the straight wire that carry a current is 0 in the textbook. And we just see that the conclusion is this: the electric field is this. And if you put L into infinity, when L tends to infinity, the electric field will tend to 0. But the reason is not because the wire is neutral, and when it's outside the band wire that carry a current I, the textbook told us that it's also 0, but actually the answer is this. Okay. Is there any questions or?
Anyone have questions? No, I feel like I'm sharing a conference. 像我很好像在主持研讨会。Does anyone have any questions? From my point of view, I think this research is really good. It's considering something that we ignored before. We just, when we were analyzing the charged wire, and then we just directly assume that it's straight and long, and then we jump into the conclusion that this is neutral and distribution is evenly distributed. But if you think about it a little bit more deeper, then you can find out, wow, that is a very bold approximation. And if you think about the curved wire, if you think about the shape of the wire, if you think about the length of the wire, then you have to consider the charges which stack themselves in the edges or which irregularly distributed in the band wire. And then you have to rethink about your calculation, and you have to derive it. And then and I think the most important thing is when you do the derivations here, and then from this one, this is a very, very careful derivations, but you can just try to compare it to the old one. And then if you put the length of the wire a bit longer, and then if you change the conditions for the geometry and then back to the original case, and then you can get the original answer. So I think, which means that this theory is more general than that one. And I think this kind of concept is very important when you are really doing research. 我用中文再讲一遍，我奇怪。这很重要的是说，你看他的这个研究啊，他之所以厉害，就是他把一些我们在做 approximation 的时候忽略掉的条件，把它重新考虑进来，然后他做了一个新的推导。但是他推导出来这些公式之后呢，如果你在他的参数里面带入这些简化的条件，你还是可以得到跟原来一样的结果。这种状况的意思就是说，他的想法跟他的理论是有能够应用的范围是更广的。所以从这一步到这一步，我们就会说这是一种科学上面很大的进步，或者是研究上面一个很大的进步。对，那通常我们在做研究的时候，第一步一定是先这里先跨出去，然后再来想这件事情。对，然后呢可以给大家一点参考，这是你实际上在做研究的时候会发生的事情。So this is what going to happen when you're really doing research, is when you're using the creativity. You have to take the first step like this, and then you have to add up some other detailed thoughts and to generalize your theory, generalize your method. Yeah. So thank you, Roger. This is a really good job.
谢谢老师。
感谢他，我觉得这个分析非常的好。那么好，结束的比我预期的早。So we just finished it a little bit earlier than I think. We have 10 minutes left. I just started a little bit of the black body radiation. We are in hurry. 我们现在有点进度有点赶，所以我们再标一段。So we just introduced wave properties of light and particle properties of light, and now we are combining them. We are treating them as a whole, and we are going to work on the wave-particle duality. And this is just the beginning of quantum mechanics. I will introduce the black body radiation and photoelectric effect. Then the Compton effect is for your final exam. So I will just simply tell you the meaning of it.
but the detailed method, and then you can just read the paper, because black body radiation, I think this is a true breakthrough for the quantum mechanics. And photoelectric effect is very important for electronic design. There are many electronics based on photoelectric effect. So I'm going to do a introduction on it. And Compton effect is usually related to radiations and particle physics, and those who work on high energy objects. And I think in normal life and in everyday life, it's not very significant. So let's just skip it and leave it to someone who is very interested. And matter wave. This is very hypothetical. This is very theoretical. But we have to talk about the matter wave to combine the interpretational wave and interpretational particles. So we do it anyway. Then when we understand everything, then we can start to work on how to calculate it, how to manipulate it, how to analyze it. And then we are going to introduce the wave mechanics created by Schrödinger and matrix mechanics created by Heisenberg. And then we are going to discuss what is the uncertainty principle and why is it necessary. Okay. So this is how we do it. And black body radiation. First, I show you several objects which gives you black body radiation. The first of them is the candlelight. If you see the candlelight, and you can see different colors, and then you can measure the temperature of different parts of the fire. And some of them, then you can see the relation between the colors and the temperature. We have this is 6, you can see that this is 600 degrees and this is 1400 degrees. It's hotter and hotter and hotter. And they have different colors. They have blue, they have yellow, and yellow or almost white. And here are some parts that you almost cannot see the color. So this is a kind of black body radiation. And this is a typical case of black body radiation. So this is the gas. Gas is generally transparent, but when it's very hot and when the molecules are running around and they are creating radiations, and the radiations get into your eyes and your brain, your nerves sense it as blue light. 这我觉得瓦斯炉是一个非常经典的 black body radiation。瓦斯本身是没有颜色的。但是你给它加热，然后瓦斯的空气就是会一直震荡，然后那个震荡就会开始有辐射线会放出来，然后那个辐射线穿过你的眼睛，刺到你的大脑的时候，你的大脑会把那个信号解读成它是蓝色的，这就是 black body radiation. And the typical case is another typical case is a light bulb. So the original color of the tungsten wire is black. 就是 tungsten wire 钨丝本身是黑色的。But when it's very hot and when the atom is vibrating, it's creating the radiation. The radiation is so strong and you sense it as yellow or orange. Then this is the lava from volcanoes. 火山喷出来的熔岩。我想应该这世界上应该没有人知道温汤的熔岩是什么颜色，应该没有办法看到，因为它的黑体辐射太强了。And the stars, and this is a very the stars are generally they are hot gases somehow gathered together by the gravitation of their spins, and if the temperature of the stars, if the nuclear reaction in the star is different and then they have different temperatures, then you see different colors. And here are the ancient people when they are looking at the stars and they start to have some imaginations. So this is Orion, 这是猎户座, and the yellow star is the stake, and this one, the bright star, is the tip of the sword. And here are the blue stars, and now we know it's black body radiation, so we can just look at the colors and we can say what is the temperature of the star, and then we can do some derivation, what are the nuclear reactions in it. Okay, cases and microscopically, what is black body radiation? So this is actually black body doesn't really exist in nature. Black body is a very theoretical thought of a perfect object to do research, and black body is just something that only do absorption, so any kind of light on it get absorbed, and it doesn't reflect, it doesn't do refraction, there is no transmission, so it's just like a big black hole. But that kind of thing doesn't really exist in nature, and everything, I think anything can reflect something. 对，我好像没有看过有东西是不会反射任何光线的，这样有点奇怪。但总之呢，黑体其实是一个在理论的推导上面一个有一点完美化的一个物体。但是它是为了推导理论方便，所以呢，他做了这样子的假设。假设这样子的东西存在的话，那一个本身会把所有的光线都吃掉的东西，假设说它自己发出光来的话，到底是什么状况呢 ？So in this kind of black body, if there are some light going out from it, then what exactly is it? And this is the hypothesis. That is because the charge carriers in the black body is vibrating due to the heat. 就是你如果加热进去的话，然后你加热进去，你可以想象我们上学期的最后一堂课，我们讲说热学有没有？然后你的原子跟分子吸了热之后，它会开始震动啦、转动啦、扭动啦，就那件事情啦。哦 ，and when it gets harder and harder and harder, so the vibration gets faster. And the collision gets faster too, and therefore the frequency of the oscillation is higher, and one of the motion just get transmitted, and more carriers got activated, and therefore we have higher radiation intensity. And we just said a little bit about it, that the vibrating charges will emit radiations, and radiation is just the changing electric and magnetic field, and it's transmitted through the space. So this is the sources, and this is how the radiation is generated. And the radiation can have a lot of wavelengths because there are so many combinations of different kinds of vibrations, and they have a very wide spectrum from wavelength. This is wavelength from 0 to 3 micrometers, and you can go on if you want to, and just it's just a band of them is in the range of visible light. So visible light, this is the wavelength of the visible light, like 400 nanometers to 700 nanometers, and you can see the colors of the wavelength just as a mark. And here is if the wavelength is shorter than violet, then this is ultraviolet. The human eyes cannot sense it, but it really damages your gene. Okay, and here are the infrared. So this is also something that you are not able to see it with your eyes. But if the water in your cell got activated by the infrared, and then it get harder. And this is how it related to your senses. And if you have different temperatures of your black body, and the distribution of the color spectrum is different. So if it's 2000 K, this is the distribution of the waves from black body. And when the temperature gets higher, then you can see the tip of the distribution is shifted to the visible light range, and the intensity of the light is getting bigger and bigger and bigger too. So if your black body is got really, really hot, and then you can see that radiation from it is very strong and very bright. So that is the increasing intensity. So this is the spectrum of black body. And here is a more detailed spectrum. And you can see the position of the tip, and you roughly have an idea about the general color of your black body. For example, at 3000 K, then it is more or less red, because in the most of the light, the biggest intensity is with red. And for this one, this is yellow, and for this is 10,000 K, this is blue. And usually when we are designing the LED lamps, we are using these temperatures to describe the color of the light. 就是省电灯泡 LED 灯泡，我们会用几度来描述光的颜色。当然，那个光实际产生的机制呢，跟黑体辐射一点关系没有。实际上，那个 LED 灯泡的颜色是涂在上面的荧光染料产生的，并不是 black body radiation。可是因为 black body radiation 是一个非常自然的标准，所以我们会使用那个色温，有一个字叫色温，我们会用色温去当做一个创造灯具颜色的一种标准啊。So when you are looking at the specs of your light bulb, and then it's telling you about the colors, it's not telling you this is white, this is blue, or this is red. No, it's not. Way. It's telling you the color temperature. So you can see that if you like clean and light blue light, like a sci-fi movie, and then you can choose a 7 or 8K light bulbs. And if you like a natural light, and then this is the numbers that you have to choose. And if you like warm light, and if you like the yellowish light, just like the original tungsten light bulb, then you have to have something like 4000 K. So this is what you can pay attention to when you are choosing your light bulb. Okay, and then next time, so let's just understand. So this is what it is. This is what we measured from. This is we do experiment, and this is what we get. And we'll stop here for today. And in the next lecture, then I will start to tell you so what's wrong with it. Actually, it's the experimental result is not wrong. What's wrong is with the theory. 所以我们今天先停在这边。那下一次我会跟大家介绍理论到底出了什么问题，然后为什么变成量子力学会窜出头的一个破口。好，我们今天先上到这边，感谢大家。